Somewhere inside the Department of Energy, a search has just begun for a machine that does not exist yet. Not a prototype, not a lab demo, a specific working quantum computer powerful enough to actually matter, and Washington has just put a government deadline on finding it. This is the uncomfortable part nobody in the announcement wants to say out loud. Right now, in 2026, there are at least 6 completely different types of quantum computers being built by competing companies around the world, using 6 fundamentally different pieces of physics. Most of them will not be the one that wins. Some of them may never work at meaningful scale at all. And the United States government just committed itself, on paper, with a hard deadline, to figuring out which one actually does. This is not a story about whether quantum computing is real. It is real. This is a story about a much harder question, one that even the physicists building these machines cannot fully answer yet. Which version of it survives? That question is not academic curiosity. It has real financial weight behind it right now. The global quantum hardware market, still relatively small in absolute terms, reached somewhere between roughly $1.8 and $3.5 billion in 2025, and industry projections expect that figure to climb toward $20 billion by 2030, growing at a compound annual rate above 40%. That is the kind of growth curve that attracts serious capital, serious government attention, and serious risk of overcorrection in either direction. Bet too heavily on the wrong architecture at this stage, and billions of dollars in public and private investment could end up funding an expensive dead end. Bet too cautiously, spreading resources too thin across all 6 approaches at once, and the country risks falling behind a competitor willing to concentrate its resources more decisively. Let that sink in for a second. 6 live, well-funded, aggressively marketed approaches to the same technology. Billions of dollars already spent. And the honest answer, even from insiders, is that nobody knows for certain which one crosses the finish line first, or whether any of them get there in the form we currently expect. To understand why this hunt is even necessary, you have to understand what all 6 approaches are actually trying to solve. A quantum computer works by holding information in a state called superposition, where a qubit can represent multiple values at once instead of a single 1 or 0. That property, combined with something called entanglement, lets a quantum machine explore an enormous number of possible solutions simultaneously, instead of checking them one at a time the way a classical computer does. The catch is that superposition is extraordinarily fragile. The moment a qubit interacts with heat, vibration, stray electromagnetic radiation, or almost anything in its surrounding environment, that delicate quantum state collapses and the calculation fails. Every single one of the 6 hardware approaches competing right now is really just a different engineering answer to the exact same question. How do you keep a piece of matter or light in a fragile quantum state long enough to actually compute something useful with it? Nobody has found the perfect answer yet. Some have found very good partial answers, each with a different fatal weakness attached. Here is what actually happened in plain terms. On June 22nd, 2026, President Trump signed an executive order titled Ushering in the Next Frontier of Quantum Innovation. Buried inside its technical language is something called the Quantum Computer for Application Development and Discovery Science Effort, an initiative built specifically to establish, at a Department of Energy facility, a quantum computer at a scale intended to initiate what officials are calling the era of quantum-enabled scientific discovery. Read that phrasing again slowly. Not a quantum computer. A quantum computer at a scale intended to actually matter. The order does not name a winning technology. It does not pick a hardware type. It essentially tells the federal government, go find the one that works, and do it through structured partnerships between government agencies and private industry. That is the hunt. And the government has given itself 180 days just to update the strategy, guiding how that hunt gets conducted. The order does something else just as important, something that sounds boring on paper but explains the entire premise of this story. It directs the creation of a national benchmarking center tasked specifically with developing consistent standards to measure quantum computing performance. Here is why that detail matters more than almost anything else in the entire document. Right now, there's no single agreed upon way to compare a superconducting quantum chip against a trapped ion system or a neutral atom machine against a photonic one. Different companies report different metrics, using different methodologies, often chosen specifically because they flatter that company's particular hardware. Washington is essentially admitting in an official government document that it currently cannot reliably tell which quantum computer is actually better than another. That admission alone should reframe how you read every quantum computing headline you've ever seen. The Secretary of Commerce, though even the order itself does not fully clarify how this new center will relate to quantum measurement technology. That ambiguity is not a minor bureaucratic detail. It suggests that even the people writing this order were still working out exactly how independent, rigorous quantum benchmarking should actually function inside the federal government in real time while drafting the very document meant to create it. Now understand what the government is actually choosing between, because this is where the story gets genuinely fascinating. There are, broadly, 6 major hardware approaches competing for dominance in 2026. Superconducting qubits, trapped ion, qubits, neutral atom qubits, photonic qubits, silicon spin qubits, and a handful of specialty platforms, including topological qubits. Each one solves the same fundamental problem: building a machine that can hold information in delicate quantum states long enough to compute something useful using a completely different piece of physics to do it. And each one comes with its own serious, unresolved weaknesses. Start with superconducting qubits, the current frontrunner in raw qubit count, and the approach used by both IBM and Google. These are tiny circuits cooled to temperatures colder than deep space, often below 50 millikelvin, using dilution refrigerators that cost millions of dollars each. Google's Willow chip made headlines in late 2024 for achieving something called below-threshold error correction, meaning that as the chip scaled up, its error rate actually went down instead of up, a milestone the field had. Whole picture. Superconducting qubits are notoriously fragile. Their quantum states can collapse in fractions of a second, and scaling them to the millions of physical qubits many researchers believe are needed for truly transformative applications remains an enormous, unsolved engineering challenge. Some real applications are already emerging from this approach even before the scaling problem gets fully solved, which is part of Ingelheim on early drug discovery simulations. IBM has worked with JP Morgan Chase on financial modeling applications that run on Envisions, the kind requiring millions of stable qubits. They are narrower, near-term demonstrations, proof that the technology already produces some real value today, long before it reaches the scale a national quantum strategy is aiming for. Now compare that to trapped ion systems, the approach favored by Quantinuum and IonQ. Instead of tiny superconducting circuits, these machines suspend individual charged atoms in space using electromagnetic fields, then manipulate them with lasers. The trade-off is almost the mirror image of superconducting hardware. Trapped ion qubits are remarkably stable and precise. Quantinuum's H-series has demonstrated gate fidelities above 99.99% on single qubit operations, a level of accuracy superconducting systems have struggled to match at comparable qubit counts. But that's not even the hardest part of this approach. Trapped ion systems are slow. Every operation requires carefully choreographed laser pulses, and controlling enough lasers simultaneously to scale these machines to thousands of qubits has proven extraordinarily difficult. IonQ once promised quantum supremacy by 2025. As of 2026, the company has demonstrated chains of only around 32 trapped ions, a fraction of what true scale would require. Read that again, slowly. One approach is fast but fragile. The other is precise but painfully slow to scale. Neither has solved the other's problem. There's a deeper engineering trade-off hiding underneath that comparison, one that explains why this is not simply a matter of throwing more money at whichever approach currently looks ahead. Superconducting. Circuits are built using techniques borrowed directly from the existing semiconductor industry, which means they can, in theory, be manufactured at large scale relatively quickly once the underlying physics is solved. But every additional qubit adds another potential point of failure, another tiny circuit that needs to be individually calibrated and kept exactly cold enough to function. Trapped ion systems avoid much of that calibration nightmare because every single ion of a given element is, by the laws of physics, functionally identical to every other one. The trade-off is that controlling those ions requires an ever-growing web of precisely synchronized lasers, and laser control does not scale the same forgiving way that printing more circuits onto a chip does. Two completely different bottlenecks, both equally real, both still unsolved at the scale this order is asking for. Then there is neutral atom computing, arguably the fastest scaling modality on the board right now, led by companies including Quera, Atom Computing, Pascal, and Inflection. Instead of ions held by electric charge, these systems trap individual neutral atoms using tightly focused laser beams arranging them in precise grids. Some neutral atom systems have already demonstrated over 1,000 atoms in a single array, numbers that dwarf what trapped ion systems have managed. But that's not even where the real risk sits. Neutral atom computing is younger and less proven at the application level than superconducting or trapped ion hardware. Scaling fast on paper does not automatically mean scaling fast into something that reliably solves real problems. One additional detail makes this modality particularly interesting for a national strategy, weighing multiple bets at once: neutral atom. Systems can, in principle, be reconfigured into different geometric arrangements between calculations, essentially reshaping the physical layout of the machine to better match whatever specific problem it is being asked to solve. That flexibility does not exist in most other hardware types, where the physical arrangement of qubits is largely fixed once the chip is manufactured. Whether that architectural flexibility translates into a durable long-term advantage or simply adds another layer of engineering complexity without proportional benefit is still being actively debated among researchers who work directly with these systems. Photonic quantum computing takes an entirely different bet. Instead of trapping physical particles at all, it encodes information directly into pulses of light traveling through optical circuits. The appeal is enormous. Photonic systems do not need the extreme cooling that superconducting hardware requires, since light does not lose its quantum properties the way charged particles interacting with their environment tend to. Companies pursuing this path, including newer photonic startups now going public, argue this makes the approach fundamentally more scalable in the long run. But that's not even the biggest question mark here. Photonic quantum computing remains less mature commercially than superconducting or trapped ion systems, and building reliable, error-corrected photonic processors at meaningful scale is still largely an open research problem rather than an engineering one. There is also a subtler advantage photonic computing holds that rarely makes it into headlines. Because photons travel at the speed of light through optical fiber, photonic quantum systems are, in principle, naturally suited to being networked together across long distances, connecting multiple smaller quantum processors into one larger effective machine rather than requiring every qubit to sit physically adjacent to every other qubit on a single chip. If that networking approach eventually works at scale, it could sidestep the single-chip scaling wall that superconducting hardware currently runs into. The word doing the heavy lifting in that sentence is eventually. Nobody has demonstrated it working at the scale this executive order is describing. And the underlying error rates in current photonic systems remain higher than what most researchers consider necessary for serious scientific applications. Electrons trapped inside modified silicon chips, built using manufacturing techniques adapted from the existing semiconductor industry. In September of 2025, a company called Quantum Motion delivered what it describes as the first full-stack silicon CMOS quantum computer to the UK's National Quantum Computing Centre, a milestone for a modality that has historically lagged behind in raw qubit count. The argument for silicon spin is manufacturing scalability. If quantum chips can eventually be built on the same production lines that already make ordinary computer chips by the billions, the scaling problem that plagues every other approach could theoretically disappear. That is still largely a bet on the future rather than a proven present. Think about what that bet actually means in practical terms. Every ordinary laptop, phone, and server chip on the planet is manufactured using decades of refined silicon fabrication expertise, factories capable of producing billions of nearly identical, extraordinarily precise components without direct human intervention on almost every unit. If silicon spin qubits can eventually be integrated into that same manufacturing pipeline, the industry would not need to invent an entirely new supply chain from scratch the way superconducting, trapped ion, and neutral atom approaches largely have. That is an enormous structural advantage on paper. The problem is that today's silicon spin qubit counts still trail well behind the other leading modalities, and nobody has yet proven that the extreme precision required for quantum coherence survives the transition onto a mass manufacturing production line the way it survives inside a carefully controlled research lab. And then there is the most controversial approach of all, the one that best captures exactly why this entire hunt is so uncertain: topological qubits, based on something called Majorana zero modes. Here's the pitch, and it is a genuinely beautiful piece of physics on paper. A topological qubit, in theory, would be inherently protected from the environmental noise that causes errors in every other quantum approach, potentially eliminating the need for the massive error correction overhead that other hardware types require. Where researchers currently need tens or even hundreds of physical qubits just to create a single reliable logical qubit. Microsoft has bet heavily on this approach, and in February of 2025, the company announced Majorana 1, described at the time as the world's first quantum processor built on topological qubits. But that's not even where this story gets uncomfortable. The announcement triggered significant ongoing scrutiny from physicists across the field, many of whom questioned whether the underlying evidence for genuine Majorana zero modes was as solid as the announcement suggested. This is not a new pattern for this particular approach. Microsoft had already invested heavily in topological qubits back in 2021, only to face what many in the field consider one of the most significant disappointments in modern quantum computing history, when earlier claimed results did not hold up under closer examination. The company is trying again. Whether this second attempt succeeds where the first one stumbled remains a genuinely open question, one that serious physicists are still actively debating today. This pattern matters far beyond just one company's reputation, because it is precisely the kind of episode of national benchmarking. Center is meant to prevent from repeating at taxpayer expense. When a private company overstates a result, investors lose money and the company's stock takes a hit. When a government commits federal research infrastructure, benchmarking standards, and who placed a more diversified bet. That is the exact scenario the entire executive order is quietly trying to avoid, even if it never says so in those direct words. Now understand why Washington built a benchmarking center instead of simply picking a winner. It could not pick a winner. Nobody currently can, with real confidence. This is not a small technical footnote. This is the entire premise behind why the executive order treats the hunt for a scientifically meaningful quantum computer as a structured interagency effort instead of a single funding decision. The order does not tell the Department of Energy to buy a superconducting machine or a trapped ion machine or a topological one. It tells the government to build partnerships across the industry and figure out, using consistent, still-to-be-developed metrics, which approach actually delivers. It is worth remembering that this hunt is happening against the backdrop of an already crowded federal science agenda, not in isolation. The same broader push toward accelerating American scientific discovery through emerging technology also includes a separate initiative launched by the Trump administration back in November of 2025, aimed at using artificial intelligence to speed up how research itself gets conducted across multiple fields, quantum computing among them. Seen together, the strategy becomes clearer. One track uses artificial intelligence to help researchers sift through the flood of experimental data these 6 competing quantum approaches are generating. The other track builds the physical hardware and the benchmarking standards needed to judge what that data actually means. Neither track works especially well without the other, and both are now running on government-mandated clocks at roughly the same time. A recent academic assessment published in 2026 evaluated 6 major hardware platforms using something called technology readiness levels, a framework originally built by aerospace engineers to judge how close a technology is to real-world deployment. The paper's conclusion was blunt. While some quantum systems are already accessible today through public cloud platforms, truly transformative applications, the kind capable of simulating complex chemistry or breaking modern encryption, could require millions of physical qubits operating with error rates far beyond what any current system has achieved. That paper reportedly took a full 2 years of peer review before publication, an unusually long process that itself signals just how contested and high stakes these claims have become inside the physics community. That 2-year review process is worth sitting with for a moment. Peer review exists specifically to catch errors unsupported, claims, and overstated conclusions before they enter the permanent scientific record. A paper taking twice the typical review length usually means reviewers found something worth arguing about, line by line, before agreeing it was safe to publish. In a field this another round of federal funding, that level of scrutiny is not bureaucratic slowness. It is the scientific community's own version of the benchmarking center Washington is now trying to build at the government level, just operating through journals and review boards instead of executive orders. Here is the sentence that should genuinely worry you, or at minimum make you skeptical of the next flashy quantum headline you see. Quantum computing has spent roughly 2 decades being described as 5 years away. In 2026, error-corrected machines are finally shipping to real customers, and photonic startups are going public, and the field is unmistakably maturing. But maturing is not the same thing as solved. The gap between a working demonstration and a machine at the scale the government now says it wants to build remains enormous, and closing that gap could still take years, regardless of which hardware type ultimately wins. It means you catch these hardware stories before they turn into government policy, weeks or months before most outlets even notice the underlying documents exist. So what happens if Washington backs the wrong horse? Funding, benchmarking standards, and interagency partnerships around 1 or 2 hardware approaches, rather than letting all 6 compete freely, carries real opportunity cost if the chosen approach turns out to be the 21st century's version of Microsoft's earlier topological stumble. Move too early, and the federal government could end up funding a dead end while a completely different, less politically favored lab quietly builds the machine that actually works. Committing resources. Chinese state-backed quantum programs are simultaneously funding superconducting processors through institutions like USTC, alongside dedicated neutral atom research through groups like KS Cold Atom Technology, hedging across multiple hardware bets at once, rather than picking one horse early. If the American strategy narrows too quickly around a single, favored approach, and that approach stalls the way earlier topological claims once did, the country risks losing ground on every other hardware front. It deprioritized along the way. This hedging strategy is worth sitting with, because it directly contradicts the instinct many people have when they hear national strategy, the assumption that a country should simply pick its best bet and commit fully. China's approach suggests something closer to a venture capital mindset, applied at the scale of an entire government, spreading serious resources across multiple competing technologies specifically because nobody, including the country's own top physicists, can say with confidence which one ultimately pays off. Whether the United States adopts a similarly diversified approach, or instead concentrates its resources more narrowly around the handful of hardware types furthest along today, may end up mattering just as much as how much total funding either country commits. This is precisely why the benchmarking center may end up being the single most consequential piece of this entire order, more than the flashier language about building a scientifically meaningful quantum computer. Before the United States can commit serious, long-term resources to one winning approach, it first needs a trustworthy, standardized way to measure whether any given machine is actually making genuine progress, rather than simply generating an impressive-sounding press release. Right now, that standardized measurement effectively does not exist. Companies self-report metrics they chose specifically because those metrics flatter their own architecture. A government-run benchmarking authority, if it is built honestly and stays independent of industry pressure, could finally give policymakers, investors, and the public a way to cut through years of competing marketing claims and actually see which machines are real. Consider how differently the last decade of quantum coverage might have unfolded if a credible, independent benchmark had existed from the start. Every major announcement, from quantum supremacy claims to record-breaking qubit counts to below-threshold error correction, would have been measured against the same fixed yardstick instead of each company effectively grading its own homework. Investors deciding where to put billions of dollars would have a shared reference point instead of competing press releases designed to look most favorable in isolation. Government agencies deciding where to direct federal research funding would be working from comparable data instead of marketing materials dressed up as technical white papers. That absence of a shared yardstick is not a minor inconvenience. It may be one of the biggest reasons hype and genuine progress have become so difficult to tell apart in this field over the past several years. There is also a quieter, more uncomfortable possibility worth naming directly. What if no single hardware approach wins cleanly at all? A growing number of researchers now suspect the future of quantum computing may not look like today's smartphone market, where one dominant architecture eventually crushes its competitors. It may instead look more like today's classical computing landscape, where different hardware types persist indefinitely because they excel at genuinely different tasks. Superconducting systems might remain the fastest option for certain narrow applications. Trapped ion machines might stay the most precise choice for specialized scientific calculations. Neutral atom systems might dominate specific simulation problems nothing else handles as efficiently. In that version of the future, the entire premise of hunting for one single machine that matters most may itself be the wrong framing. The real answer might be several different machines, each mattering for different reasons, none of them ever fully replacing the others. That possibility does not appear anywhere in the executive order's language, and it probably would not photograph well for a press conference. Governments generally prefer announcing a single winning strategy over admitting the honest answer might be considerably messier and less politically satisfying than a 5-minute signing ceremony can capture. There is a version of this outcome that is genuinely optimistic, even if it complicates the tidy narrative. A world with several coexisting quantum architectures, each specialized for different problems, is not necessarily a failure of strategy. It could simply mean the technology matured the way most complex technologies eventually do, through specialization rather than a single conqueror. Classical computing itself never settled on one universal chip design either. Different processors dominate phones, servers, graphics rendering, and industrial control systems today, each optimized for what it does best, and nobody considers that outcome a disappointment. Quantum computing settling into a similarly specialized landscape would not mean the hunt described in this executive order failed. It would simply mean the government eventually needs several different benchmarking standards instead of one, and several different winning strategies instead of a single triumphant announcement. That reframing matters for anyone trying to follow this story honestly over the coming years. The measure of success for this executive order was never going to be a single clean headline announcing one victorious quantum computer. It is far more likely to be a slower, quieter accumulation of benchmark reports, agency alignment plans, and incremental funding decisions, each one narrowing the field slightly, none of them dramatic enough on their own to make the evening news, but adding up over years to whichever answer eventually emerges. Still, the search is now officially underway. Backed by federal deadlines, a national strategy currently being rewritten, and a benchmarking center tasked with finally answering the question the entire industry has quietly avoided for years. Which of these machines is real, and which of them is still, essentially, a very expensive, very promising physics experiment? History offers a useful, if slightly humbling, comparison here. Early classical computers went through a remarkably similar period of chaotic hardware experimentation before silicon-based transistors eventually became the industry standard almost everyone recognizes today. Vacuum tubes, mechanical relays, and multiple competing memory technologies all had their moment of genuine promise before quietly falling away, one by one, over roughly 2 decades of trial and error. Quantum computing may simply be repeating that same messy pattern now, just compressed into a considerably shorter and far more geopolitically charged timeline, with 2 competing superpowers instead of one country working the problem largely alone. That earlier transition offers one more lesson worth remembering before this story ends. The technology that eventually won the classical computing race was not necessarily the one that looked most impressive in its earliest demonstrations. Vacuum tubes were, for a period, faster and more established than the fragile early transistors competing against them. Transistors ultimately won, not because they started ahead, but because they proved more reliable, more manufacturable, and more scalable over time. Exactly the qualities the current quantum benchmarking effort is now trying to measure honestly for the first time. The lesson is not that today's frontrunner in qubit count will necessarily lose the way vacuum tubes eventually did. The lesson is that raw, early-stage impressiveness has historically been a poor predictor of which technology actually wins in the end. Before you go, if breakdowns like this, the kind that actually explain the physics instead of just repeating the headline, are useful to you, go ahead and hit subscribe, because this channel keeps digging past the press release every single time a story like this breaks, long before the mainstream coverage catches up to what the actual documents say. So go back to that phrase buried in the executive order one more time. A quantum computer at a scale intended to initiate the era of quantum-enabled scientific discovery. Nobody in Washington can currently tell you which physical technology actually delivers that outcome. Superconducting, trapped ion, neutral atom, photonic, silicon spin, real sense, auditioning for the same role at once, and the government has essentially admitted it does not yet have a reliable way to judge the performance. What is certain is this: most of these approaches, according to the researchers actually building them, cannot all succeed at the scale this order envisions. Some will hit walls that better funding cannot solve. Some will turn out to have been oversold from the very beginning, the way earlier topological claims once were. And one, or perhaps a combination of several, will eventually become the machine an entire era of scientific discovery gets built on top of. Nobody knows yet which one that is. Not the physicists running these experiments in their own labs. Not the companies spending billions to convince you they already know the answer. And, as this order itself quietly admits, not even the government now formally tasked with finding out. Maybe that admission is actually the most honest thing to come out of Washington on this topic in years. Every previous quantum announcement from every company involved has arrived wrapped in the confident language of certainty, a specific chip, a specific milestone, a specific claim of supremacy. This executive order, for all its bureaucratic language and interagency, structure essentially concedes the opposite. It says, we do not know yet, and here is the machinery we are building to eventually find out. In a field this crowded with overconfident marketing, that kind of institutional humility, whether intentional or simply a byproduct of drafting a document nobody could fully agree on, might end up being exactly what this technology needed all along.